Welcome to this explainer. If you've been developing in Python for, well, really any length of time, you absolutely know the headache of environment management. It's kind of like a rite of passage for us, right? But today, we're dropping the ultimate production-ready blueprint that might just leave that chaos behind for good. I mean, look at this. For years, we've just dealt with this historically fragmented, chaotic landscape. We use pip for packages, ven for isolation, pyin for versions. Honestly, it was exhausting. But then, Astral's Rust-backed tool UV arrived on the scene like an absolute lightning bolt. It essentially consolidated this entire landscape. And the kicker? It runs up to 100 times faster than those legacy tools. But here's the thing. Lately, I've been hearing a really dangerous myth from folks. They ask, if UV manages my Python versions and dependencies perfectly, why do I even need Docker anymore? Doesn't UV make it obsolete? Okay, let's dive into this. Because today is a masterclass on why these two tools aren't competitors at all. In fact, they actually create an unstoppable combination. Section 1. The division of labor and why they must coexist. To really understand this, think about deploying your app as being a lot like shipping a super fragile electronic device across the world. In this setup, UV is your internal, custom-molded foam padding. It operates entirely inside the Python language space, making sure your dependencies match perfectly down to the exact cryptographic pin. But it assumes the underlying operating system is already there and working. Docker, on the other hand, is the heavy-duty ocean shipping container. It handles the operating system primitives, the file systems, the network configs, the whole shebang. When you look at this feature breakdown, you can really see the gaps. UV simply cannot fetch native OS tools like a C++ compiler or libpqdev, and it can't manage network ports. Docker handles all of that for us. Listen, without Docker, your lightning-fast UV environment on a Mac is probably going to crash on a Red Hat Linux server because of missing OS libraries. And without UV, your standard Docker builds become horribly slow and brittle. You literally need both. Moving on to Section 2, the 3 golden rules of optimization. Now, what's really interesting about this slide is that it shows you can't just write a standard Docker file if you want to unlock V's maximum speed. You have to follow a few rules. Rule number 1 is to mitigate hard links. See, UV usually saves a ton of disk space locally by creating hard links from its internal cache. But inside isolated Docker storage layers, yeah, that can cause some nasty invalidation bugs. So we force a copy mode using UV_link mode equals copy to make it play nice with standard Docker storage drivers. Next up, rule number 2, mount the cache using Docker build kit. Standard Docker builds just wipe away temporary caches to keep image sizes down. But if you do that here, changing a single line of code means you're basically re-downloading the entire internet. This rule ensures Docker actually remembers your downloaded packages across builds. And rule number 3, pre-compile bytecode ahead of time. Python usually compiles code the very first time it runs. But the crucial point is, doing that during the Docker build completely eliminates cold start latency. When you're spinning up transient containers in production, they are going to boot up almost instantly. It's a real game changer. All right, Section 3, the multi-stage blueprint. Let's zoom out from those rules and look at the overall architecture, because this is how we drastically shrink both the attack surface and our total disk space footprint. It's a simple 3-step flow. In Stage 1, we extract the stable upstream UV binary. In Stage 2, our builder stage, we lock down our environment and install dependencies using those lightning-fast cache mounts we just talked about. And finally, Stage 3 isolates a minimal production runtime. We copy over exactly what we need and secure the whole thing utilizing a non-root system user. It's clean and it's highly secure. Finally, Section 4, multi-service coordination. Because let's face it, modern systems don't live in a vacuum. We need operational databases, maybe task queues, which means we need orchestration via Docker Compose. When we wire things up, we use inner service lifecycle hooks. And this brilliantly illustrates how we guarantee our Python Web API safely waits for PostgreSQL to fully initialize on port 5432. We don't have to rely on fragile, hard-coded IP addresses anymore. We get a totally secure virtual network bridge using container host names. So, what's our grand takeaway from this explainer? Well, UV and Docker are not competitors. They are two halves of a complete, rock-solid modern development stack. By combining the Rust-driven speed of UV with the immutable isolation of Docker, engineering teams are literally reducing container assembly times from minutes down to seconds. That is huge. The days of struggling with broken environments and endlessly slow builds are officially over.
The tools are here, and now you've got the masterclass blueprint. So, I'll leave you with this. How will you refactor your next deployment stack?